Hello, this is our video presentation for Fluid Dynamics Project 2. On this slide, you can see a diagram of our system. What we have is a water tank filled with water. At the green circle here is a gate. The gate opens, water is allowed to flow through the tank, through the tube. The tube has a varying length. You can see that the tube is angled and not actually at the green point parallel to it. When we did our calculations, this angle was consistent. We found that the height difference between the bottom of the tube and the green point is only 0.4 centimeters. This is a 4% total height change, so therefore we ignored it and assumed in our model that the green point is also the lowest point of the tube. Some equations that we need to use to model this flow through the tube, what we're interested in is as this length changes, what is the time to drain considering everything else is constant. We are using the Bernoulli's equation plus the friction losses and the minor losses. For our particular system, the pressure on both sides are equal, so those cancel. The velocity at the very top of the tank is 0, so that goes to 0. And then cleaning up, moving the heights to the left-hand side, we get equation 1. Equation 2 here is simply the volumetric flow rate, which is the area of the tube times the velocity going through the tube. At the bottom here, we have our equations to calculate our loss factors, our Reynolds number, and our friction factor. To model the time to flow, what we did was take equation 1 and we rearranged it in terms of velocity here. And then we took equation 2, which is also, we can model it as the change between the area of the tank with respect to the height of the water as it changes with time. We are assuming that the mass flow rate through the tube changes with respect to how much water is in the tank, because as you have more water in the tank, the pressure going through the tube would be greater. So as the water drains, our mass flow rate will become slower. In order to model this, we had to take an integral between the height of the full height and the drained height of the tube, and then as well as time. So we took equation 3 and 4 here, set them equal to each other, moved the time variables to the left, moved all the height variables to the right, took our two integrals, we're left with a t on the left-hand side, and we're left with just our constant z heights on the right-hand side. When we rearrange this for t, we are given our physical model that we are using to predict the time of flowing. This is for the straight tube model. If we want to use the t-joint, we would just add an extra minor loss coefficient next to this k to model the t-joint. This slide, you can see our system properties. On the left, all of this was given. We had to find the density and viscosity for water. On the right, we are assuming that the tube is made out of PVC, which is this will lead to this roughness factor. The inlet of the tube to the tank is sharp edge, so our minor loss would be 0.5. The T-joint is threaded and dividing branch. We assume that. That means we have a factor or a coefficient of 2. And our Reynolds number, once we were doing all our calculations, the minimum we found was 8,180. This is greater than the 4,000, thus we have turbulent flow in our tube. We are using Excel to model our system. You can see it here on the sheet that we just have all our constants listed, as well as the length of the tube, which we can change, and our relative roughness we are calculating. The velocity we're calculating here is simply equation 3 here. Our Reynolds number is this Reynolds number equation, and our friction factor calculated is this friction factor. Since the friction factor needs to have the Reynolds number is looking for the velocity, and the velocity is looking for a friction factor to calculate. We calling each other, it'll be a circle, and we couldn't do this calculation. How we got past this is by having two friction factors, the one we calculate and initial one that we guess. So we guess a friction factor, that means we can guess a velocity and Reynolds number, and that means we can guess a calculated friction factor. We then wrote a macro, which looks between this friction factor cell and the calculated one, and iterates until they're within 3 decimal places of each other. So when I click this button, they'll iterate between 3 decimal places. Now we have our predicted velocity, our predicted Reynolds number, and our actual calculated friction factor. Now we can take all of those numbers in the cell or in the sheet and calculate the time to drain, which is simply this equation right here. The cell, I can change it to be 0.6 meters. You can see that our guess friction factor and our calculated one has changed. I run the macro again, and now this is our time for 0.6 meters. We have the same thing for the T-joint. It's the same exact sheet. The only difference is we add this extra K coefficient for the T-joint. Going back, we can see our predicted versus experimental times. We found that the predicted and experimental for the 20 centimeter length were very close. For the 60 centimeter length, they were 20 seconds off. We were faster in our predicted time. This could be due to the experimental tube not being perfectly straight, not having the same roughness we were predicting, a whole bunch of factors, but we think that 20 seconds is quite good, so our model, we believe our model is quite good as well. For the straight tube with the T-joint, we found that for 20 centimeters, it would be 4 minutes 31. For 40 centimeters, would be 4 minutes 54. Makes sense that if you add the T-joint, it will be much slower than what you will have with the straight, because the T-joint adds extra minor loss coefficients as the water has to flow through it, and the momentum changes, which means you lose the potential energy due to friction. Thank you.